So, as you can see here, when we talk about DC transient analysis, we have two types of analysis. Okay, so the first analysis we call it as a first order circuit, and the second analysis is we call it as the second order analysis. Okay, so for transient analysis, okay, for the first order circuit, why we call them as a first order circuit is because inside that circuit it contains only one storage element, whether capacitor or inductor. Okay, and based on that configuration, we call them as the first order circuit. Okay, let me check. Uh, can you hear me well? Because I'm in the meeting room. I cannot talk too loud because it will disturb everyone else inside here. All right. So when we are dealing with the first order circuit, okay, we have two conditions. Okay, the first condition where your circuit, we call it as a natural response, where this particular natural response can be determined at the infinity um, time, where your circuit at that particular time frame, okay, there is no sources connected to that circuit. So that particular circuit, we call it as a natural response circuit. Okay, and the other types of the first order circuit, we call it as the step response, where after t equal to zero circuit, okay, that particular circuit connected to the sources, whether voltage source or current source. So in your syllabus, okay, we only cover the circuit that having the independent source only. Okay, we have no dependent source. All right. So as we know that the transient analysis circuit, it always contains a switches. Okay, whether you have one switches, two switches, or combination of double pole and single pole switches, and so on. So before you are able to analyze that particular circuit, you should know where is the circuit or where is the switches located after t equal to zero and before t equal to zero. All right. So when you look at the past year's questions, okay, you always see this kind of switches. Okay. So this is the essential steps when you are analyzing the transient circuit, whether the first order circuit or the second order circuit. So when you look at the first switches, okay, so as you can see, the red arrow, okay, is going down and they've been labeled as t equal to zero. The arrow is going down. So for that particular switches, it carry the definition of when the switch or when the circuit is before zero, okay, when it's before zero, the switch is open. So before zero condition, switch is open. Okay, so the switch will look like this. It's open. All right. But after zero, for the first configuration of the switch, okay, after zero, the switch will be closed. If you fail to analyze where the switch is located, whether it's open or closed, then the whole of your analysis is gone wrong. Okay, so that's why I say analyzing whether the switch is open or closed or located at B pole or at A pole is the most essential steps before you can analyze further your circuit. Okay, if you have any problems in analyzing the switch, okay, so you need to sit down and relax, look at the switch and arrow carefully. Okay, where the arrow is going, whether going up or going down, okay, going to the left or right. It depends on the circuit. All right, so the switch is closed. for the second condition after 0 seconds. All right, so let's move to the next switch. Okay, so for the next switch, okay, as you can see, switch number 2, okay, is the same single pole switch, okay, but the arrow, okay, is going out or going up. All right, so in this particular scenario, before 0 seconds or before t equal to 0 or t less than 0, your switch will be closed. Okay, and the switch is like this. Okay, and when it's after 0 or t equal to 0 or t greater than 0 or t approaching infinity, okay, your switch is open. Okay, so this is the switch. Looks like it's open. Okay, now, okay, let's move to the switch number 3. Okay, for switch number 3, okay, we have a double pole switch. Okay, where it can move from A to B or B to A. So based on this configuration, okay, for before 0 circuit or T less than 0, the switch is located at A. Okay, and the switches will look like this. This is A. Okay, and it's not connected to B. And after 0, the switch will be moved to B. Okay, B. So this is how the switch looks like. It goes to B, right? And for the last switch configuration, okay, the fourth switch configuration, before 0 or at t less than 0, okay, your switch is at B, okay, okay, so this is the switch looks like. So this is your B point, okay, and after 0, okay, or t equal to at t equal to 0 or after 0 seconds, the switch is at A. All right. So based on this switch configuration, do you have any questions? Um, I encourage you to just interrupt me when you have any question because I cannot look at your chat during I did my presentation. Okay, if you have any question, just interrupt me and ask your question. All right. So next step, okay, on how to tackle the first order circuits question is by following this step to solve the first order circuit. Okay, so to those who are already in my section, I always introduce them or already introduce them or always ask them to follow this particular steps because by having or by following this step, you are not doing some careless mistake by leaving the most important parameter not being calculated. Okay, So to solve the first order circuit, whether it's RL or RC circuit, okay, so at step one, what you need to do is you need to analyze the circuit at t before zero. Okay, so when the circuit is at t before zero, the circuit is fall under steady state condition. Okay, so you need to remember when the circuit is fall under steady state condition, your storage element, which is C or L, okay, will behave differently. Okay, as for the capacitor, it will behave like an open circuit. All right, and for the inductor, it will behave like a short circuit. Okay, so these are the things that you need to remember very well. Okay, for the capacitor, it will behave like an open circuit during steady state condition, and the inductor will behave like a short circuit during steady state condition. And at step one, okay, at step one, what you need to do is to find the initial value. Okay, so these are the purpose of having a step one. Okay, so in this particular step, you are required to find the initial value for V across capacitor or the current that flows through the inductor. Okay, if you have the RC circuit, so you need to find the initial value of the voltage across the capacitor. Okay, and if you have the RL circuit, you need to find the initial value of the current that flow through the inductor. Okay, if you see that the circuit also required or request another parameter other than the storage elements parameter, just leave it aside first. Focus on solving your storage elements, um, storage elements equation. Okay, whether V or I depends on it's RC or RL. All right. So that is the first step. All right. Next one. Move to the next second step. At step two, this is where you are analyzing your circuit at t after zero. Okay, so at this moment, we are assuming that your circuit is approaching infinity where it's fall at the steady state condition. Okay, so at step two, the circuit must be the circuit after zero. Okay, so the circuit must be the circuit after zero, and we analyze the storage element under the steady state condition. Okay, so at step two, all right, you can have two types of condition. All right, the first one is a natural response. Okay, where at natural response, as I mentioned earlier, okay, your circuit is no longer connected to the sources. Okay, the other type is a step response where your circuit after 0 seconds is connected to the sources, whether current or voltage. All right. So when we have a natural response, okay, our I infinity or V infinity is equal to zero. Okay, because it's not connected to the sources. There is no one will supply any VOI to them. Okay. But for step response, okay, your circuit after 0 seconds is connected to the source, where at this moment you will definitely have the value of V and I. Depends on what type of circuit, which is RL or RC. Right? After the step two, the next step that you need to do is the step three, where at this moment we are analyzing the circuit at transient. Okay? At step three, you should use, okay, you should use circuit at t after 0 seconds. Okay. At step 3, you should use the circuit at t after 0 seconds. And from that particular circuit, okay, you need to find your R equivalent. Okay. If you have a natural response, you don't have any problem with that. Okay. But if you have a step response, the sources is connected to your circuit. So what you need to do before to find the R equivalent, you need to turn off the sources. Okay. For voltage source, when we turn it off, it becomes short circuit. Okay. For current source, when we turn it off, it becomes open circuit. All right. So to find the R equivalent, okay, we turn off the sources first if we have the source, and we take out or remove for a while your capacitor or inductor, and then find the R equivalent from that capacitor or inductor point of view. Okay. And then after finding the R equivalent, the next parameter that you need to determine is the tau. Okay. So the tau, the name of tau is a time constant. So for RC circuit, the time constant equation is R times C. And for RL circuit, the time constant equation is L divided by R equivalent. All right. And the unit of the time constant is seconds. And the final step in solving the first order circuit, okay, we need to write a complete transient equation where the complete transient equation, it depends on what parameter that you are required to determine, whether V or I. Okay, so the general equation of transient response complete equation is the V transient plus V final. Okay, so in your exams, whether test or final exam, the general equation of first order transient equation will not be given, will not be provided. Okay, the only equation that will be provided to you is the second order transient equation. Okay, so do you have any question before we move to the example? Right, so let's look at this past year's test question. Okay, I'll make it bigger so you can see it clearer. All right, so this is a last semester test question. Okay, let's look at the question one, where question one is for first order circuit. So in this particular case, when we see figure Q dot one, okay, we can see that in this particular circuit, we only have R and L elements. So obviously, this particular circuit is the RL first order circuit. Okay, and based on the question, you are required to determine the inductor initial value, the inductor current final value, and you also need to determine the resistance current. Okay, the 6 ohm, the current that flows through the 6 ohms. Right, this one. Okay, and then after that, you need to come out with the transient expression, the complete expression of your IL, and also the complete expression of your IR. Okay, and then you need to plot both responses, and then you need to compare between the response of IL and IR. Okay, so by looking at this question, this is how we should solve it. Okay, so based on this circuit, since we should determine the initial value, so this particular initial value is fall under step 1. Okay, so where at step 1, you should draw or sketch the circuit before 0. So based on this switch configuration, okay, before 0, okay, the switch is at location 1. Okay, before 0, the switch is at location 1, right? So this is the circuit will look like. All right. So based on this circuit, you need to come out with the value of inductor initial current, okay, and also the resistor initial current. Okay, so at this particular step, we can apply the Ohm's law to find the I total. This is your I total. And then after that, use your current divider to find IL. So this is your IL. Okay, and then after that, to find the IR, okay, at the point that I highlighted in brown here, okay, you need to apply your KCL, Kirchhoff current law. Okay, why we need to apply the KCL? Because we want to determine the value of IR. So your IR is equal to 0.67 ampere. So don't forget to write down the unit. Next one, you need to calculate the final value, IL infinity and IR infinity. So for the final value, it falls under step 2. Okay, where at step 2, you need to sketch the circuit. Okay, yes, Muhammad Yasir, do you have any question?
Victor, can you share his slide?
Pardon?
I say, can you share his slide or reference?
I couldn't hear you clearly.
Doctor, he asked to share the slide.
To share the slide
Yes.
in PDF. The slide, I already share my screen. I think everybody can see it. Okay. So those who just came in, this is the question that we will discuss about. All right. Now, we are at step 2. Okay, so at step 2, we need to find the final value of your inductor current and also the resistor current. Okay, so at this moment, you should draw or sketch the circuit after 0. Okay, so this is the circuit after 0. Okay, so this circuit, we need to analyze it using the Ohm's law. Okay, to find the I total. Okay, this is your I total. And then use your current divider to find the inductor current. Okay, so In this particular circuit, as you can see, our inductor current is negative. Okay, it's due to the, where is my highlighter? Okay, it's due to the direction of your IT and your IL and IR. And why am I choosing my IT direction is like that? It's due to my voltage source. As you can see, the voltage source polarity is opposite. Okay, the positive is at the bottom and negative is on the top. Okay, so as we know that the current will come out from the positive polarity. Okay, all right, and based on that, okay, so based on that, when we do the current divider, okay, the current direction of IL and IR should be the other way around. Okay, should be the opposite. Okay, to follow the current divider law. And that's why we will have our IL infinity is equal to negative 2 amps. Right? And then after that, at this point, okay, we apply the KCL to find the IR infinity. Okay, we will get the value of IR infinity is negative 1 amp. All right, settle question A. Now move to question B. So in question B, okay, the question require you to come out with the expression of IL for t greater than 0. It means that this particular question require you to write down the complete expression of the inductor current. Okay, so to get the complete expression, we need to have another parameter which can be analyzed under step 3, where this particular circuit is at transient. Okay, so at step 3, okay, the purpose of having a step 3 is to determine the tau for this circuit, to determine the time constant. Okay, yes, Omar.
So the transient state is at t equals 0, yes? And
Yes, so at step 3, at transient, we need to draw the circuit after 0.
okay, so in this example, the inductor will be changed to an open circuit, and my question was regarding the capacitor. Will it be a short
Okay.
circuit?
All right. So at this transient situation, the storage element will behave like their normal um, their normal characteristic, where the inductor or the capacitor does exist. It's not being shorted or it's not being open because it's at transient. Okay. The capacitor or inductor will be shorted or open if the circuit is analyzed or fall under steady state condition. Okay, so at transient is the moment where this particular circuit are changing gradually. Okay, from one step to another step. Okay,
Okay, thank you, doctor.
all right. Okay, so at this step 3, this particular circuit, we should draw the circuit after 0. Okay, and then find the time constant. So to find the time constant, since this particular circuit, it consists of the voltage source, okay? This particular circuit, since it's connected to the voltage source, this is the step response circuit, okay? So we need to turn off the sources. So for voltage source, when we turn it off, it becomes short. Okay, so I write it down here. Turn off the source. Okay, so we turn off the source, V will become short. Okay, and then after turning off your sources, then we take out a while or remove a while your inductor. Okay, and from that inductor point of view, okay, find the R equivalent. So at this particular circuit, your R equivalent is 3 ohm parallel with 6 ohm and series with 3 ohm. Okay, these three parallel with 6 and series with the 3. Okay, and you will get R equivalent is equal to 5 ohms. Okay, after getting the R equivalent, then you can straight away calculate your time constant, right? Which is equal to 10 milliseconds. Don't forget the milli. Milli is 10 to the power of negative 3. But in writing, please don't write the 10 to the power of negative 3 or negative 6 or negative 9. Please write it down whether it's milli, okay, micro, or nano, or pico, or mega, or tera, or kilo. All right. And then after getting the last parameter, then we now able to write down our complete expression of our inductor current. Okay, where the complete expression of the current is equal to the I final plus I initial minus I final times e to the power of negative t over tau. Okay, so you insert the value of your tau, okay, the final value as well as the initial value. And finally, this is your last answer. Okay, ILT equal to negative 2 plus 3.33 times e to the power of negative 100t. From where did I get the 100? Is from 1 over 10 milli. Okay, so I write it down. This 100 is 1 over 10 milliseconds. Okay, all right. Any question? How did we get the initial? I initial. It's at the step 1. This is the step where we should calculate our initial current of the inductor. Okay, so from where did I get the 1.33 amps? Okay, it's based on this circuit. Okay, so from this circuit, okay, this is the value that I want to calculate. Okay, IL. So from there, okay, we apply our Ohm's law as well as the current divider, and then we will find that our IL initial or initial inductor current is 1.33 amps. Okay, as you can see here, this is the general equation of current divider. Okay, Yes, Omar.
Doctor,
Hmm? Eh, Khalid. Yes.
to find the current across 6 ohm, why didn't we use the current divider?
Yes, you can use the current divider as well, but what is the point? Because we already get the inductor current, then we just apply our KCL there.
But we can also use the current divider 6 ohm parallel with 3 ohm and over 6, right?
Yes, you can use it.
Okay.
Okay.
Excuse me, doctor. I just want to ask,
Yeah.
will we be able to have this PDF?
Yes, the organizer will give it to you, and then I will also pass to the organizer all the examples that we have been discussed today, and they will distribute it to you.
Thank you very much.
Okay, let's move to the next example. Okay, we are not yet finished the question. All right, so next question, question C. Determine the expression of IR. Okay, now after we getting our IL equation, now we need to calculate IR. This one, okay, the resistor current here. This, all right. So to calculate the resistance current, okay, what we need to do is, okay, since we already have the value of IL, okay, then we can just analyze the elements that I highlighted in green there, okay, where we need to find the VR, and then after getting the VR, we use our Ohm's law to find the IR, okay. So I enlarge the circuit that I highlighted in green there to become this, okay. So based on this circuit, okay, our job is to find the VR. Why we need to find the VR? Because we need to calculate the IR. Okay. At this moment, okay, after doing the analysis previously, we have the value of IL. Okay, where we can get it from here. This is your IL. Okay, so we have our IL, and then we can apply our KVL to find the VR. Okay, but how to find the VL? Okay, we need to apply the inductor law. So this is the inductor law. Okay, the inductor law said the voltage across the inductor is equal to L times the differentiation of IL towards T. Okay, so you need to differentiate your IL equation and then times with L, then you will get the equation of VL. So this is your VL. Okay, then after that, to apply KVL at this loop, we also need to determine V, which is the V across 3 ohm. Okay, and since this particular V is in series with your inductor, okay, therefore, this particular resistor will receive the same amount of current that that particular inductor received. Okay, so in other words, your resistor 3 ohm will have the same current as your inductor. Okay, So from there, we calculate our V by just using the Ohm's law, I times R. And finally, this is the equation of your V. Okay. After getting these two values, then we start to do our KVL. Okay. KVL at this loop. Okay. And then by applying the KVL, we can see that our VR is equal to this expression. All right. After getting the VR expression, finally we can generate our current expression. Okay, where V divided by R. So this is the final answer that required by your question. Okay, and then after that, at D, okay, the question required you to sketch. Okay, how to sketch? Okay, what you can do is plot the equation or the expression one by one. Okay, maybe you need to have two or three value of t and then plot it on your graph. Okay, you just sketch it, no need to be so accurate. Okay, and then from there you can get the trend of your graph. Right, after that, the last question. Okay, based on the plot in D, what is the major difference between IL and IR? Okay, so basically the main difference of these two um, sketch or these two graph is the IL, okay, have the continuity, what we call it, the continuity characteristic, and your IR is having the discontinuity characteristic. Yes, no.
Excuse me, how to how to determine the voltage the voltage is negative or positive?
How to determine whether the voltage is positive or negative?
Yeah, yeah.
Okay, it depends on the circuit. So based on this circuit, as you can see, V at the inductor, V at your resistor 3 ohm, okay, from where we get this particular negative is actually come from your current expression, this one, okay. So to determine this particular polarity, okay, you need to look at the original circuit, okay. So based on the original circuit, where is my original circuit? Based on this original circuit, okay, your IR is going down, okay. And as we know that the characteristic of passive elements, they are having a different direction of voltage and current. It's not like the active element. For passive element, which includes R, L, and C, these three are passive elements. Okay, the characteristic of passive elements is they are having the opposite direction of current and voltage. So from this particular circuit, the current that flow through the 6 ohm resistors is going down. Okay, it's going down here. Okay, so the voltage across your resistor is going up, where this is your V, where the head of your arrow carrying the positive polarity. it's always carrying the positive polarity, and the tail of your arrow carrying the negative polarity. Okay?
Okay, thank you.
All right. Okay. How can we say that the resistor current having a discontinuity? Okay. Look at this area. Okay. There is one moment where, okay, there is no voltage or no current, okay, at this area, the thing that I highlighted in yellow there, okay. There is one moment where at, where is my other color? Okay, at that, I'm using another color. Wait, okay, let me use the red one. Okay, at 0.66 m, okay, this 0.66 m is happening when t equal to 0, okay. But at the same time, okay, at t equal to 0, okay, we also have another value, okay, which is negative 2.11. So from this particular situation, we can see that the 0.66 and negative 2.11 is actually having some date time before they continue their journey. Okay, so it seems like they, let me highlight, okay, the blue graph, okay, and the brown graph are having a different identity. Okay, that's why we call this particular situation as a discontinuity. Okay, but when you look at your IL, okay, at t equal to 0, okay, we will have the same value for the orange waveform and the green waveform. Okay, clear? Who is asking? Bara'ah? Okay, so all this particular workflow, okay, carrying a 10 marks, okay, it's quite a lot, okay, but if you practicing enough, you are able to answer this kind of question less than 80 minutes. Right, so where is the next question? Do you want to have another examples on first order, or you want me to move to second order?
Yes, please one more example, if possible.
All right, so okay, so I have another examples on first order circuit. Okay, this time around we will have a RC circuit. So look at this question carefully. To those who want to snap the picture, can snap the picture of the circuit. Um, Before we move to this first order, or you want me to move the second order circuit and then we go back to the first order, or just finish with this example, then we move to the second order.
Could you please finish this example first?
Okay, we finish this first order first, then we move to the second order. All right, so based on this circuit, okay, you are required to calculate the initial voltage at capacitor and also the final voltage at the capacitor. Okay, and after that, you need to write down the complete expression of the V across capacitor and finally sketch the transient form. So this particular question carrying 6 marks. Okay, so we have a double throw or double pull of the switch. Okay, it has point A and point B, and this is the RC circuit. Okay, all right, so let's move to the step one. At step one, where t is less than 0 or t before 0, so this particular circuit at this moment is analyzed under steady state condition, where at steady state condition, your capacitor will behave like the open circuit. Okay, so this is your circuit looks like the circuit before 0. Okay, now we need to find the voltage initial across your capacitor. This, okay, and since at that particular point, okay, it's been open, so there is no current that flow through your 6 ohm. Okay, so your voltage across the capacitor is actually fall directly on the 8 ohm resistor. This one. Okay, and to find the voltage across this 8 ohm, we need to determine the value of current that flow through this 8 ohm resistor. Okay, so to find the I1, I name it as I1. You can also use any variable that you want to name it as long as you write it down clearly. All right, so use your current divider. So this is a current divider. Okay, so use the current divider rule. You will get I1 is equal to 4 amps, and then from there you calculate your V, the initial value of your capacitor, which is V at 8 ohms, which is equal to 32 volts. Okay, the next one at step 2, at step where the t is approaching infinity, and the circuit is the circuit after 0, after 0 seconds. Okay, so based on this circuit, okay, since there is no sources connected to this particular circuit, so we can call this circuit as a natural response circuit. So there is no value of your final value, where your VC infinity is equal to 0 volt. Okay, and then settle question 1 and go to question 2, where you need to write down a complete expression of your V across capacitor. So in order for you to write down the complete expression, you need to know the value of time constant for this circuit. Since this particular circuit is the RC circuit, so the time constant equation is R times C. Okay, so this is the circuit after 0. Okay, and from this circuit, there is no sources. Okay, and you need to take out your capacitor to calculate the R equivalent. So when we take out the capacitor, so the R equivalent is actually equal to 6 series with 4 ohm, which is equal to 10 ohms. Then use this formula to find the time constant for this particular RC circuit, which is equal to 0.2 seconds. And then after getting all the parameters, you can start to write down your complete expression of the V across capacitor. Okay, you will find that your VC is equal to 32 times e to the power of negative 5t. So from where did I get this 5 is equal to 1 over 0.2. Okay, and then based on this voltage across capacitor expression, you are required to sketch the circuit response graph, right? So this is how you sketch the graph. Okay. If you don't have any idea on what the trend of the graph looks like, so you need to plot it at least three points. Okay, at t equal to 1 or t equal to 2. Okay, and then from there you can get the shape, the initial shape of your graph. Then you can start to sketch it. All right. Now let's move to the second order circuit. So for the second order circuit, it's a little bit tiring because the workflow is quite long. Okay, but in your task 2, the marks is 10 marks. Okay, in your final exam later for second order question, the question might be longer because it carries maybe 12 or 13 marks. All right, so now let's move to the second order circuit. So we call this particular circuit a second order circuit is because, okay, your circuit contains both storage elements. Okay, it contains L and C together. Okay, and this particular second order circuit, we can analyze it whether it's in series RLC or parallel RLC. Okay, there is another configuration. We call it as a series parallel RLC. That particular configuration is out of your syllabus. All right. So in your syllabus, we just only focus on series RLC or parallel RLC. And same goes to your first order circuit. This particular second order circuit can fall under natural response or step response. Okay. So for the switch configuration, it's just the same like what we have discussed earlier. So I leave it blank here so that you can do this exercise by yourself. Okay, to know whether you understand or not the switch location or position when it's before 0 or after 0. All right. So in analyzing the second order circuit, I have listed down a 6 important steps. Okay. So the first step, we need to analyze the circuit before 0. Okay, where at this particular step, we need to find the initial value of I and V. It's not O anymore. It's I and V. Why? Because we have both elements. We have L and we have C all together inside one circuit. Okay, so for inductor, okay, we need to find the initial value of the inductor current. Okay, and for capacitor, we need to find the initial value of the capacitor voltage. Okay, and at step 1, we should analyze the circuit under a steady state condition. All right, then move to the step 2. Okay, so at step 2, okay, we need to analyze the circuit when the switch just moved from one point to another point. Okay, from open to close or close to open or from A to B or from B to A. The switch just moved. Where at this moment, okay, the circuit still holding the initial value that has been calculated in step one. Okay, that's why we have this continuity equation. Okay, and at this particular step, okay, we need to find the derivatives of the initial value. Okay, so we need to find the dv0 dt and di0 dt, where your dv0 dt can be determined by using a capacitor law, and di0 dt can be determined by using the inductor law. All right. Next one, at step 3, is where we analyze the circuit at t approaching infinity, where at this moment, the circuit that you should sketch or draw is the circuit after 0. Okay, the circuits after 0, and this particular circuit is analyzed under steady state condition. Okay, where under steady state condition, your L and C will react or behave like the short circuit for the inductor and open circuit for your capacitor. And at this moment, you need to find your initial value of current and voltage. Okay, if you have a natural response circuit, your final value is equal to 0. But if you have a forced response or step response, you will have your final value of V and I. All right. So next step is the longer step, okay, which is step 4. At this moment, you need to analyze your circuit under transient, okay, where at this moment, your C and L, or your capacitor and inductor, okay, will behave like their original characteristic. Okay, it means that your C and L does not short or open. It's behave like the inductor. It's behave like the capacitor. All right. And at this moment, at this particular step, okay, what you need to do, okay, you need to determine the circuit of RLC, whether it's series or parallel. Okay. After you determining whether the circuit is series RLC or parallel RLC, then you need to calculate the value of alpha and omega naught. Okay. After calculating alpha and omega naught, okay, by using this equation, okay, this is the equation of alpha and omega naught, depends on the types of your circuit, whether it's series RLC or parallel RLC. And this particular formula will not be given during exam. You need to memorize it. Okay. So after getting alpha and omega, you need to compare these two variables and determine whether your circuit falls under overdamped or critically damped or underdamped. Okay. And then at this particular step also, you need to write down the characteristic equation depends on your circuit damping response. Okay. For the overdamped response, this is your characteristic equation, and this is the transient equation. Okay. If your circuit is fall under critically damped response, okay, so this is your characteristic um, parameter, which is S1 equal to S2 equal to alpha. And this is the transient equation. Okay, and if your circuit is fall under damped response where your alpha is smaller than omega naught, okay, and your roots become a complex conjugate roots where at this moment when your circuit is fall under damped response, so you need to find another additional parameter which is called omega d by using this formula, okay, and then write it down into your transient equation. Okay, so as you can see, your transient equation here, I write it down as x, okay, x and x. Why I write it down in x is because it can either be your voltage or current, okay. So for example, if the question asks you to find the voltage, then you replace the v with the x with v. If the question asks you to find the current, replace the x with I. Okay, it's going to be the same transient equation. So after you write down your transient equation, okay, based on the damping type, at step 5, you need to write the complete response equation where the complete response equation consists of the transient equation plus the final value. Okay, so the final value, where we can get the final value, it's under the step 3. This is where the final value being calculated. All right. And then after that, okay, at step 6, okay, step 6, I can call it as the optional step. Depends on your question. Because some questions, they are not require you to calculate or solve the coefficient of A1 and A2. But some questions, they are required you, okay, to calculate the coefficient of A1 and A2. It depends on how many marks, okay, the question. All right. So if the question require you to calculate or solving the coefficient A1 and A2 or B1 or B2, okay, you need to have these two equations. Okay, depends whether I or V. Okay, if you are analyzing the current equation, so you need to have IT and the IDT equation. Okay, or if you are analyzing the circuit for V, okay, you need to have the equation of V and dVdt. All right, then you need to solve this equation, whether V or I, at t equal to 0, okay, where you need to use the value in step 1 and step 2 to solve the coefficient value. Okay, any question regarding the steps? So when you look at the step, it may look simple, it may look difficult or complex, okay, but if you do a lot of exercise, okay, then that particular 6 step will become a little bit easier for you to do it. All right, so let's move to the next example for second order. All right, so by looking at this question, okay, this is the last semester's question for test 2. Okay, as you can see, the statement that I highlighted in yellow there, this particular question require you to solve A1 and A2. Okay, so let's look at the question 2A. So you need to calculate or determine these 4 items. Okay, the initial value of current, initial value of voltage, okay, and the derivative initial value as well as the current final value. Okay, so let's solve this particular question. So the initial value of I, L, and VC, okay, we can get it from step one. So at step one, we need to analyze the circuit before zero. And this particular circuit is fall under steady state condition where your capacitor is open and your inductor is shorted. Okay, and analyze the circuit by just using your basic law. You no need to apply your method of analysis here. Okay, just use your Ohm's law and um, yeah, just the Ohm's law, right? And find your IL initial and VC initial, which is equal to 0.5 amps and 15 volts respectively. All right. Next one. Okay. So in this particular stage, okay, we need to move to the step two because in the question, they require you to find the initial value of your derivatives element. Okay, so that particular value can only be determined under step two. Okay, so at step two, the switch just move. Okay, and the circuit is the circuit after zero. Okay, so write down your continuity equation. All right, and then this is the circuit after zero. Okay, after 0 second circuit. Okay, where at this moment you need to bear in mind that your capacitor is still holding their initial value at step one, and your inductor still holding the current initial value that has been calculated at step one. Okay, so at this particular stage, we need to find the VL and IC. Let me highlight it with another color. Okay, so we need to find IC and we need to find VL. Okay, right. So to find IC, okay, it's a little bit easier because this particular circuit is a series circuit. Okay, and your IC, okay, having a different direction of your IL. So your IC is equal to negative IL, right? And your IL0 is equal to 0.5, where your IC is equal to negative 0.5. Then, by applying capacitor law, okay, this is the capacitor law, I at capacitor or I that flow through the capacitor is equal to C dVc0 dt. Okay, and from here, we find our dVc0 dt is equal to the current at capacitor divided by the capacitor value, which is equal to negative 62.5 volt per second. Next one, we need to find the V across inductor. So to find the V across inductor, okay, the only option that you have is to apply the KVL. Okay, apply the KVL. So do the KVL. Okay, so negative V across capacitor plus V across the 30 ohm plus V across the inductor and plus V across the 20 ohm. Okay, so this is your KVL equation. Okay, and finally you will get the value of V across inductor is negative 10 volt. Okay, then by applying your inductor law, so this is the inductor law. Okay, V across inductor is equal to L times DIL dt. Okay, so by having this value, we know that the value of DIL0 dt is equal to negative 2 amps per second. Right? Then at step 3, where at this moment we are analyzing the circuit after 0. Okay, and at this moment your circuit is fall under steady state condition. Okay, and when the capacitor and inductor is analyzed under steady state condition, the capacitor is open, the inductor is shorted. And since this circuit is a natural response circuit, there is no sources connected to this circuit. So your final value both for V and I is equal to 0. Okay, so write it down like this. And then question B, find the value of alpha and omega naught and determine the type of response. So for question 2B, this particular value is fall under step 4. Okay, where at this particular step, your circuit is at transient. Okay, when the circuit is at transient, your capacitor and inductor is behave like their original characteristic. So based on this circuit, it's clearly seen that your R, L, and C is in series. Okay, therefore, the formula of alpha is R over 2L and omega naught is equal to 1 over square root LC. Okay, then calculate the value of alpha and omega and compare these two elements. So by comparing these two elements, we can see that alpha is equal to omega naught. By having this condition or parameters, we know that our RLC circuit is fall under critically damped. Okay, where for critically damped, your S1 and S2 equal to alpha, and your transient equation for current, from where did I know my transient equation is current, is based on this circuit. This circuit, but this is question. They are require me to calculate or write down the complete expression of current. Okay, so from there, okay, I know that my transient equation is current. So this is the transient equation for critically damped. Okay, all right. And then after that, after write down your transient equation, move to the step 5 to write down the complete equation or complete expression of your I for the second order circuit by adding the transient. This is the transient equation, and this is the final value. Final value is equal to 0 because of this circuit is natural response circuit. All right. And since the question asks us to find or solve A1 and A2, okay, so we need to have these two equations. Okay, we need to have the original transient equation and final value, which is the complete response, IL, is equal to A2 plus A1t times e to the power of negative 5t. Okay. And DIL dt, you need to differentiate this expression. Okay. You need to differentiate this expression to become this. Okay. After getting these two equations, now we should analyze both circuits under t equal to 0. Analyze ILT and DILT over dt at t equal to 0. Okay, where IL0 value is equal to 0.5, where we can get this particular value at step 1. Okay, from step 1. Okay, and this particular value from step 2. Okay, right? The IL0 over dt is equal to negative 2 m per second. Okay, so replace all the t's here, t, this t, and this t, and this t. Where, okay, this t that highlighted in orange, replace it with 0. Okay, and then you will get A1 and A2. This is A1. Okay, A1 and A2 equal to 0.5. After getting A1 and A2 value, write again the complete expression together with the A1 and A2 value. Okay, any question? I hope you're clear enough on how to solve second order circuit questions. Right, so inside this notes, okay, I give you another two examples for second order question. Okay, you can do it by yourself. Okay, and then refer to my notes for the solutions. Okay, so before I end the class, so do you have any other question regarding second order or first order? No questions?
Uh, I just have a small question, please, regarding uh,
Mhm.
what if we had a negative number under the root? How will we write the
For,
equation with the complex number?
for the complex number, or is do you mean that your circuit is fall uh under them?
Yes.
Okay, so for under them, what you need to do, this particular example is for, yes, okay, now this is the example for the under them. All right, as you can see for under them, okay, your roots is a complex number. Okay, so you just need to leave the roots there. Okay, but you need another parameter that we can call it as the omega d. These are the value that you needed for the underdamp. Okay, and then this particular omega d, you need to insert it to your complete response or transient response equation. But what if you have the um, overdamp? Okay, So let me show you the example that I have done in my class. So this if you want the example that I did in my class, you may ask from the student in section 1. Okay, so let's look at this. So this particular example is for under overdam response. Okay, so this is overdam response. So for overdam response, okay, as you can see that your root value is equal to negative 0.264 and negative 4.736. So what you need to do, okay, when you have your transient equation, you just write it down, the value that you get. Okay, there. Okay, Oma?
Okay, doctor, thank you very much.
All right. So any other question before we end the class?
Thank you very much, doctor, for the revision.
All right. All right. So if you don't have any questions, so thank you so much for attending this revision class. So I hope that you clearly understand on how to tackle the first order and second order question. Okay. And I wish you all the best for your test too. Thank you.
Uh, Again, doctor, how will we get the PDF?
I will give the PDF to the organizer and then they will distribute it to you.
Okay, okay, thank you very much.
All right.
Thank you very much, doctor.
Okay. So thank you so much, guys.
Thank you so much, guys, for joining today, and good luck for your test.
All right.
Thank you, doctor,
All right. You're
for the
welcome.
revision class.
Okay. Thank you.